Hello, everyone, and welcome back. What I want to do now is very briefly touch upon the LP convergence of Fourier series. So last time we very conclusively discussed the L2 theory of Fourier series, and that was, I don't want to say it was easy, but it was comparatively easy because of the theory of Hilbert spaces. So the LP theory is quite a bit harder. So let's first kind of reformulate the problem of convergence of Fourier series. So, first, to do that, I'm going to make a very trivial note that if Sn is a partial Fourier series operator, it's clearly a linear operator. Sn acting on F is linear. Then the operator norm from LP to LP, P is anything between 1 and infinity, including 1 or infinity. This is less than or equal to 2n. And the proof is very straightforward. So all you need to do is write down what SNF is. It's the integral f of x minus t dn of t dt for f1 periodic. Smash in absolute values. So remember what dn even is. Dn was this sum here from minus n to n, e to the 2 pi I k x. So trivially, if you just smash in absolute values, you're going to get, actually it should be 2n plus 1, but it really doesn't matter. So you just smash in absolute values. Right, this becomes 2n plus 1. And then if p is infinity, you just throw the L infinity norm of p out if p equals 1. Just because of the 1 periodic property, do a change of variables. This is the L1 norm of f. Otherwise, if p is strictly between 1 and infinity, just use Holder's inequality, and then do a change of variables. And you get the LP norm of f over 0 to 1. Okay. And again, it's not that it matters at all, but this really should be 2n plus 1, 2n plus 1. OK, so let's put this to good use. So, right, so we don't really, so for this lemma, we're not going to allow p to be infinity. And we already know that we don't have convergence of Fourier series for p equals infinity. We exhaustively, or we very carefully looked at divergent, we proved a nice divergence theorem about the existence of continuous functions whose Fourier series diverges on a prescribed prescribed countable set. So certainly then you don't have L infinity convergence for these functions. And we proved that such functions for any prescribed countable set are dense in space of continuous functions, so quite a few of them. OK, so we claim that we have LP convergence of Fourier series if and only if the supremum of these operator norms are bounded. And this is a really important idea to somehow translate a convergence problem into a problem involving taking soups and somehow, boundedness of some either operator or family of operators. And you do this a lot of times in different areas of mathematics, particularly analysis. You want convergence properties of something. You prove that, or not so much, you reformulate it in terms of proving boundedness of a certain operator or boundedness of a certain family of operators. Okay, and the proof is quite nice. It's a very easy proof. So half of the proof is basically principle of uniform boundedness. So remember what the principle of uniform boundedness, if I have two Banach spaces, X and Y, actually, I think one of them, I forget, I think maybe Y can be a norm space. Or anyway, let's just say we have two Banach spaces, X and Y. Then having a pointwise bounded family of operators, in the sense that for any X, sup, Tnx, and norm is bounded. Now, the bound might depend on X, but that's OK. As long as for each fixed X this is bound, that implies that you actually have a uniformly bounded operator norm sequence of maps, a sequence of operators. And Tn's assumed linear. OK, so let's say X is Y is LP. This is certainly a Banach space. We haven't proved it, but basically it's very easy to prove. And it's the Banach space. Let's say Sn is, well, just a partial Fourier operator mapping F to the partial Fourier sum. We proved that this is a bounded linear operator. Initially, all we know is that the operator norm depends on n. It's 2n plus 1. OK, so right, so for F in LP, so we're assuming here that this is true. So we're going to assume that this is true. So pick some big N, most certainly, sorry, pick some big M, most certainly possibly depending on F, where N bigger than M means that this is less than, we don't have to be fancy here, 1 works. Anything works. OK, so we can get a fairly trivial uniform bound on, so maybe go to black here. It matters, but yeah, so let's get a nice trivial uniform bound on SNF. Right, so if n is between 1 and m, just use that trivial bound we got. The operator norm of Sn is bound by 2n plus 1, so this is less than or equal to 2n plus 1 LP norm of F. And that's, well, n is less than m, so this is less than 2m plus 1. Whereas if big N is bigger than m, then just do the triangle inequality. We know this is bounded by 1, so this is just bounded by 1 plus the norm of F. Okay, so right, we get this. We get this bound here for all n of 2n plus 1 times f, norm of f, the maximum of that, and 1 plus norm of f. So the norm here is just the LP norm on 0 to 1. Right, so yeah, so this is for each, so for each fixed f, this supremum is finite. Certainly depends on f possibly, because initially m is going to depend on f. So by the principle of uniform boundedness, actually this operator norm is uniformly bounded. Okay, so let's do the other direction. And this is quite interesting. We're actually going to use what we had last time, particularly Fourier's theorem, for the converse. So what I just proved actually works for p equals infinity. No issue there. But the converse does not. So for the converse, we proved that the span of these exponentials is dense in LP. Particularly, so remember what we did last time. I didn't explicitly, well, I mean, we proved this and mentioned this for p equals 2, but so sigma and f, remember in the last video, we proved, well, it's not much to prove. It's the average of the partial Fourier sums, and hence it's trivially in the span of these complex exponentials. But sigma and f is an S, and sigma and f converges to f in LP 0 to 1. Remember, if p is between 1 and infinity. Okay, so yeah, so the span is dense in LP. So let's pick some epsilon positive and pick G in the span of these complex exponentials where this norm here is less than epsilon. Okay, so let's write G as the sum here. Yeah, just G is in the span, so it can be written out like this. And this is a little, didn't come out too well, so let me just fill this in real quick. All right, that's quite a bit better. Okay, so let's figure out what Sn of G is. Well, that's just, like anything else, it's just G hat of K e to 2 pi I kx. Okay, so really quickly, it's pretty trivial, but just to make sure we're all on the same page, let's figure out what G hat of K is. Well, remember G of x is the sum here, L equals minus n. Let me just double check that. One second. Yeah, okay, sorry about that. So G is, right, the sum here, e to the 2 pi I Lx. Okay, so G hat, well, just by definition, multiply this by e to the 2 pi I kx, or sorry, multiply by minus e to the minus 2 pi I kx, and integrate 0 to 1. So it's CL e to the 2 pi I Lx e to the 2 pi I kx minus. And as usual, we can just combine this into one exponential. So it's e to the 2 pi I L minus k x dx. Sorry, I just don't know why I put that CL there. Okay, well, right, so this is fairly trivial. We have two possibilities. K is between minus n and n, in which case L will be k in the sum here. And this just collapses to 1. So this is going to be ck if k is in this interval here and 0 otherwise. So if k is bigger than n. Okay, so right, so this collapses down to ck and k. Well, unless k is between minus n and n, this is 0. Well, that is what g of x is. And this is true as long as big N is bigger than little n. So that we, if big N is bigger than little n, we'll capture all the CKs. Otherwise, there's going to be some of them that are never picked. Okay, so in other words, Sn is just the identity for or at least, sorry, SNG is just G. And this is extremely powerful to know. Okay, so let's just look at this norm here, SNF minus F. Let's add and subtract SNG. No harm there. SN is linear, so it's SNF minus G. And then I added here, use triangle inequality. And all the norms here are the LP norms on 0 to 1. Well, this is G. Okay, we can just do the operator norm, pull that out. And we know we're assuming this is uniformly bounded by some CP that depends on P. And we know that we chose G so that these are both less than epsilon, or rather just this norm here is less than epsilon. So it's CP plus 1 epsilon, where CP is independent of F. Okay, so I mean, we're not claiming N is independent of F. N depends on little n. Little n certainly depends on F, because G depends on F. But at the very least, this proves that for this fixed F, we can let n go to infinity, and the lim sup is less than any epsilon. Yeah, lim sup is less than any epsilon. So, right. Okay. Right, and that the key, of course, was that well, we're assuming that this operator norm is independent of n. If we just use the crude trivial bound 2n plus 1, we cannot let n go to infinity. I mean, 2n plus 1 times CP plus 1 times epsilon, as n goes to infinity, I don't care how small epsilon is, that still goes to infinity. So the fact that this is independent of n, which is our assumption, proves it. Okay, this is not easy to do. You can, in a relatively elementary way, prove this. You can prove that this here too is true using complex analysis. This was proved by F. Rees, the same Rees from functional analysis, Rees representation theorem, in the early 1900s, I think, the first decade. But yeah, that uses complex analysis, and we're not assuming any complex analysis. And more importantly, as I mentioned, you want proofs in Fourier analysis independent of complex analysis when you can get them, because you really can't extend complex analysis easily to higher dimensions. And you would want to, possibly extend results in Fourier analysis to higher dimensions. We would get into that if we had more time. So, coming up with proofs that more resemble, measure theory, which is fairly trivial in higher dimensions, is very much desirable. And yeah, we'll return to this in a little bit. So yeah, so to be continued. So what I want to do now is get into the Fourier transform. So there's quite literally thousands, probably, of books that discuss the Fourier transform. On the other hand, there's only one book that I know of, and this is a nice book. I mentioned this before, Fourier series by Tolstov, the cheap Dover book. It's very heavy on the applications of Fourier series, and it's really at a level of just assuming basic analysis, no measure theory or anything. So it's a unique book. But what this book does, and what I'm going to do, is show you how to derive the basic formulas for the Fourier transform through Fourier series. In other words, I'm going to answer the question, where the hell does the Fourier transform come from? It's just this magical thing that is nice. No, it actually is literally like Fourier series for an L2 function on the real line or an Rn. Okay, so let's talk about that. And I'm just going to do, when I'm doing things informally, we're just going to do things on the real line. I'll carefully prove stuff for the Fourier transform in Rn because it's so important in all different areas. And we'll do an example on how Fourier transform in the next video is used in the theory of PDEs. We'll derive what's called the Bessel potential. Yeah. Okay, so Fourier transform as a limit of Fourier series. So let's say f is an L2. So the key fact here is the absolutely trivial consequence of the dominated convergence theorem is that if f is an L2, the Lebesgue integral of f squared is this limit here as L goes to infinity minus L to L. This is absolutely trivial. Your dominator is modulus f squared, characteristic function, minus L to L. Okay? So why is this profound and why is this important for us? Well, we proved that complex exponentials are an orthonormal basis for L2 of 0 to 1. You can just absolutely trivially translate and dilate to use that to get you a orthonormal basis for L2 of really any interval minus L to L suffices for us. And this is really easy. I'm just giving this for a homework. I'll collect it in the future homework. Yeah, it really, I mean, there's a lot of different ways to do this. All of them, assuming you have, assuming exponentials are a nice orthonormal basis for L2 of 0 to 1, like we did in the last video. Yeah. Okay. Yeah, probably checking Parseval's quality is the easiest thing to do. Remember, you have like this whole laundry list of, something is an orthonormal basis, is equivalent to this, equivalent to that, blah, 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 blah. All right, so let's put this to good use. Okay, and so the key here is that I can expand this L2 norm in terms of a Fourier series. So let's do exactly that. Okay, so yeah, so this here is just the Fourier coefficients on the interval minus L to L, so it's a minus here. So remember that's just F E K L2 minus L to L, where the EKs are these complex exponentials here. Okay, so what I'm going to do is very fuzzy. I'm not proving I'm not proving the isometry property of Fourier transform. I'm not proving the inversion formula. I'm just deriving them in a way that informally comes from Fourier series. So yeah, I don't want to hear comments, oh, this is not rigorous, you're cheating a lot. I am. We will prove all those two properties in the next video, but again, I want to just derive where the Fourier transform comes from and the two most important properties of it informally from Fourier series. So because we're letting L go to infinity here, let's just informally assume L is infinity. It's approximately infinity. So I have this here, and I'm multiplying and dividing by 2 here. So if you've seen a Fourier transform already, well, you will recognize that we have a Fourier transform. We simply put, there is a Fourier transform here. And in particular, we're plugging in K over 2L into a Fourier transform. So if you've never seen the Fourier transform before, well, so here it is. So there's some issue with, well, wait a minute, f is L2. Why does this integral exist? I mean, let's assume f is in. Let's just assume f is in L1, intersect L2 for the time being. I mean, everything is informal, so I don't really care about convergence. But if you really want to be sure that this integral exists, well, really all you need is f is in L1, and then just because absolute value of this obviously is less than or equal to absolute value of f of x, because this is a complex exponential, it has modulus 1. So yeah, f is an L1, and this is a perfectly well-defined function for each u. But anyway, so let's say this is f hat. So what I have here is f hat of k over 2l, or in other words, f hat of xk. So you might be seeing where this is going here. We're setting this up as a Riemann sum. So let's say delta x is xk minus 1, which is just 1 over 2l. So we have partition points, and we're partitioning the real line by these little tiny intervals where the interval length is 1 over 2l. And L is going to go to infinity, so we'll get an integral informally when L goes to infinity. So what I have here, well, anyway, so let's say this whole thing here, maybe I'll erase this here. Let's call this star. Okay, so right, 1 over 2l is my delta x here. And I obviously get the 2l from squaring the 1 over square root of 2l. This is f hat of xk. So, right, this is literally a Riemann sum. And the picture here is just a usual Riemann sum picture. You know, let's say, so let's say this y value here is f hat of xk modulus squared. And this is, let's say, a graph of modulus f hat of x squared. So yeah, this is just the Riemann sum. We're finding the area under these rectangles. And the length of each interval is very small, 1 over L. So as L goes to infinity, we get an integral. We're doing this because it's from k is minus infinity to infinity. We're doing this over the whole real line. So we've derived very, rigor be damned, but at least we've shown, where the Fourier transform comes from. And we've shown that it is natural to think that the Fourier transform should be an isometry on L2. Now let's informally derive a formula for Fourier inversion. This is actually a little easier. Same idea. Let's say x is in the real line. Pick some positive integer L bigger than absolute value of x. And let's just say FL of x is, well, it's f of x. Well, it's f of x times characteristic function. And if L is bigger than absolute value of x, then this is equal to f of x. So, right, so here the idea is if f is an L2, then FL, so yeah, like before, assuming f is an L2, so then this here is an L2 of minus L to L. So we can use just the expansion in terms of our orthonormal basis, basically our Fourier series. So in the L2 sense, we have FL of x is going to be this sum here. Okay, but, and this should be L2, well, the L2 of minus L. Okay, so this is a little tight here, but so what I have here is just exactly what I have here. Either 2 pi I kx over L, just, either pi I kx over L, just multiply and divide by 2. And here it's square root of 2L, square root of 2L. Okay, and yeah, so it's just F times the complex conjugate of e to the k, which is stick a minus in the exponential, and we get the 1 over square root of 2L. And we do the same thing. We pull out the 1 over square root of 2L's to get 1 over 2L. Yeah, sorry, the integrals, well, anyway. So, sorry, don't want that. This is correct. So, right, so like before, let's say we're saying k is, or xk is k over 2L. So this is going to be either pi I x xk. Again, replace this with minus infinity and to infinity. Put a 2 here. So this is, again, either minus 2 pi I this is either minus 2 pi I kt. 1 second. Yeah, sorry about that. Forgot if I put a minus for the Fourier transform or not. It really doesn't matter, as we'll see, but want to be consistent. Okay, right. So we do exactly what we did before. Basically, just replace this with minus infinity to infinity. So this is exactly the Fourier transform with k over 2L plugged in, which is xk. And so this is a Riemann sum. This is, if you want to get rid, this is literally delta x. So if you want to just get rid of this and put delta x, great. X is just a constant. So this is going to be, right, exactly what I have here. And as a Riemann sum over the whole real line, as the partition size goes to 0, this is going to be minus infinity to infinity f hat of u e to 2 pi I ux du. Okay, well, what did we start off with? F of x. And if you want to be, well, no, this is fine. No issue here. But for fixed x, remember that for large enough L, f of x is FL of x. I mean, we have, point-wise convergence almost everywhere. So really, you can pick a subsequence of L's converging to infinity, which doesn't change anything. But the point here is that we have f of x. And we did all this thanks to Fourier series. And we got this really curious formula, which is called Fourier inversion. Great. So, right. So I should quantify something here. So we usually use this notation. A backwards hat is a Fourier transform of f just plugged in, let me use x. Doesn't really matter what I use, but. So it's basically the Fourier transform. So minus infinity to infinity. f of u e to the 2 pi I u x, or xu, doesn't matter. Okay. So it's the same thing. If we didn't have a minus here, it'd be a minus here. Minus minus makes it plus. So we can succinctly write this as, and this is often how it is written, that we have Fourier inversion means that this is the inverse Fourier transform. So f hat inverse hat equals f almost everywhere. All right, so what I'm going to do in the next video is to very carefully prove these for functions that are L1 intersect L2. So in particular, we're going to prove Fourier. We're going to prove the isometry property, and we're going to prove Fourier inversion almost everywhere. Actually, we're going to do this for functions in Rn because it's actually you can reduce it to proving it actually for n equals 1. The proof I'm going to do is very standard. It uses approximate identities that we talked about earlier, particularly with the Gaussian. Right, so for higher dimensions, you define the Fourier transform of x, basically the same thing, except use a dot product, x dot u. I mean, I don't think I need to say anything here, but this is just the usual dot product, xi, ui, no complex conjugate here, x and u are real. And inverse Fourier transform is the same thing, basically f of minus x. So inverse Fourier transform is just going to be, actually, sorry, so easy to, yeah, so I do want a minus here. So easy to just switch them because they're the same thing except a minus sign. Okay, so right. So this is the Fourier transform here with the minus. Inverse Fourier transform with no minus. Okay, hopefully you enjoyed this video. Yeah, I'll put more videos to come soon. Yeah, so we're going to do this. And the next video also will define the Fourier transform for L2. It's a little, if you haven't seen it before, it's a little abstract, but it's still very important. And the general procedure, is very important on how to do it. Concretely, you can only define the Fourier transform for L1 intersect L2 for the very simple reason that, getting a little ahead of myself here. So if you define the Fourier transform in this way, well, how do you know this exists as a Lebesgue integral if f is just at L2? And the answer is it generally does not, period. So you cannot define the Fourier transform for an L2 function in this way. Sometimes it does, sometimes doesn't. In what we did above, we didn't care. Everything was informal. But if you want to do things rigorously, there are very concrete examples where this does not exist for f and L2. Well, if f is an L1, again, that's trivial. You just take, this is a Lebesgue integrable function. Absolute value is less than or equal to f of u. So you can integrate it. But anyway, all right. So I'll have a new video up very soon. So long. Take care. New homework is coming up. Sorry, I haven't been good with that, but all right. Until next time.